Those who may not be able to attend the class, for them, I will share the recorded video also after the class. Yeah. So just to recall what we have discussed. First class we have discussed linear independence. Then with the help of definition, we have defined another quantity. It's called rank of a matrix. What is the rank of a matrix? Rank of a matrix is the number of independent rows or the columns of a row of a matrix. So how do you do that? How do you find rank of a matrix? Either we find out how many linearly independent columns or linearly independent rows are there in the matrix. For a given matrix, for m by n, for row 1, row 2, and then row m, for column 1, column 2, and column n. So one thing we can do by this definition says you have to find out how many row are independent. If there are 5 row are independent, others are dependent, then we can say that this matrix has rank 5. Okay. But we have seen that if it is if the system is lengthy, that number of size of the vector is length, then we have to solve a system of linear equation of 5 by 5 or 4 or 10 by 10 order. Then it is difficult to solve those systems. Hand calculation is difficult. So we need a better way to find out the rank of a matrix. For that, what we have defined? We have defined this row operations, elementary row operations. 3 elementary row operations. With that, we have seen that what is called a row echelon matrix, row echelon form of a matrix. So it has two property 1 and property 2. Either it can all the zero row. The zero row will be at the bottom level, and then the leading non-zero entry for each row will be right to the previous row. Okay. So there is a question that if it can happen that 0, 0, 0, A1, 2, 0, 0, 0, and then A1, 3, then A2, 3, and then probably this is 0 and 0. Whether it is in REF. Question is whether it is REF. The answer will be yes, because it needs to satisfy property 1 and property 2, nothing else. So property 1 says if 0 row happens to be there, they should be at the bottom of the matrix. So this row and this row are at the bottom of the matrix. Now each leading row should be right to the previous row. So for the row 1, there is no previous row. So here the leading non-zero entry is here. For example, A12 is the non-zero entry. It is not talking about that A11 should be non-zero. It can be 0 also. So with this knowledge, we proceed further. That how do we, from linear independence, we have defined the rank of a matrix. That if number of rows, this linear independence, number of rank of a matrix, number of linearly independent rows. You can say columns also, but whenever you speak, just speak for one, not together, either row or column. Okay. Now, what we do, we have obtained this new idea that is called row echelon form. So this row echelon form will say that the rank of a matrix, okay, this rank of a matrix is the number of non-zero row in the REF, that is the row echelon form of A. So rank of A is equal to the number of non-zero rows in the row echelon form of the matrix, given matrix A. So this is how we relate the idea of row echelon form and the rank of a matrix. In the previous class, we have seen the relation between the linear independence of vectors and then the rank of a matrix. Now today we are going to see this relation. Okay. So this remark 5, it says that for a given vectors linearly independent if the REF has no non-zero row. If you go back and check the examples, so this matrix will have, by the definition, okay, this definition, the new definition, the rank of A is equals to 3. So the rank of B will be 2 here. Similarly, because all are in REF, row echelon form. Okay, so for this one also, this rank of C matrix is 2. Okay, so all three vectors, all three row vectors are independent here in this matrix. But here they are not independent. Here also, not all are independent. Okay, now how to find the row echelon form? So find the row echelon form of a matrix. Let us start with a simple example. So if you start with this example, okay, so A, let us call A, then it is 1, 3, and then 5. So 2, minus 1, and 4. Then minus 2, then 8, and then 2. Okay. So we will do row operations, elementary row operations, either E1 or E2 or E3. We will apply any one of them so that it happens to be. So what we want, let us mention that.
Sir, rank is 2, sir.
Yeah, thank you. Thank you for your quick answer. I will show how do we do it. For others, those who are still not able to solve, so let us see how do we do it. So let us keep this first row as it is. Okay. In order to get the row echelon form, what we need, we want 0 here and also 0 here. So we do one by one. If we want to make 0 here, we can see this is 2. 2 and 1. So what we will do? So R2, this row 2, let us call new, row 2 new, will be replaced by row 2 minus 2 times row 1. So if you do that, so 2 times 2 into 2 times 1. So this becomes 0. So let us put 0 here. Then minus 1 time minus of 2 times 3. So this becomes minus 7. So let us put minus 7 here. Then this one. So 4 minus 2 times 5. So this becomes 10 minus 4. So this is minus 6. So this becomes minus 6. And let us keep the third row as it is. Okay, we'll do one by one. Minus 2, 8, and 2. So this operation we can write R2 minus, in simple way we can write R2 minus 2 R1. Okay. So this operation is done. First step, we have got 1 0 in the desired position. The next step is to get 0 here. We want to make it 0. So how do we do that? We will take the help of R1. So R3 minus, so minus 2 times. So let us call it plus 2 times R1. So if you do that, so 1, 3 and 5, they keep remain same. 0, minus 7 and minus 6 are same. Then if you write, so this is minus 2 plus 2 times of 1. So this becomes 0. So let us put 0 here. Then 8. 8 is there plus 2 times of 3. 8, 2 times of 3. So this becomes 14. So let us write 14 here. And then 2. This is 2 plus 2 times of 5. Okay, 2 times of 5. So this becomes 12. So this is 12. Let us write 12 here. Okay, so the first column we can see that we have satisfied that property 1. But we have to satisfy the property 2 also. No, property 1 is not satisfied here. So property 1 or property 2, if there is a non-zero leading entry for the row 2, we have leading non-zero leading entry is minus 7. And we want 0 also here. So next step, what we do? We
Columns of
okay, right. So this is row 3. Okay, row 3 is there, 14. And then plus 2 times of row 2. If we do that, so what we will have? 1, 3, 5. Then this is 0, minus 7 and 6. So if you go if you add these two rows, R3 is 0, 14 and 12. So now we have multiply with 2. So 2, it becomes 14, minus 14, and you add them with, so this becomes 0. Similarly, 6 into minus 2, so minus 12. So minus 12 plus 12, this become also 0. Now we can see that, so this is the row echelon form is in REF. It is in row echelon form. So what will be the rank? Rank is 2. Rank of A is 2. Similarly, if you want to find the rank of this matrix, the 4 by 4 matrix, so what you have to do is, when the concepts are clear, you know how to find REF. Now the next step is to, so since you are, this is the beginning of the course, so that is why I am doing this step by steps. But if you know all the steps properly, in order to avoid the errors, you can just directly write of this form.
Excuse me, sir.
Yes, tell me.
So I had a doubt, like, is a null matrix already present in its REF form?
No, it is not in REF because you have to think about, just a minute, I'll think about it, whether it is REF.
Okay, sir. Thank you, sir.
Yeah, you can say if 0 rows exist, then it will be at the bottom. So here we do not have any bottom sense. All, I mean, 0 matrix is all.
Yes, sir.
It satisfies property 1. Okay, but if you think about property 2, if each leading non-zero row again I am telling Rohan, what you have said that for a null matrix, that means zero matrix, A11 is zero. Yeah, it is zero, but we don't need A11 can also be zero. Coming back to you, Aditi's question, so we will. Okay. So for in order to answer the Aditi's question, so what can we say? Mm, I think it is. It can be said. It is in. So if you go back and check the property,
Okay,
the
sir.
property for each leading non-zero entry in a row is to the right uh, leading non-zero entry in the previous row.
So I have a small doubt. A11 should always be non-zero, right?
No, it is not.
No,
It is not mentioned. See,
sir
then
given.
property 1 says,
Yes,
this is
sir. The
also in REF.
yes, sir. The A11 need not be non-zero all the time. So like null matrix is already in its RDF form, I guess.
Yes. According to this sense, say all zeros if exist, all zero rows if exist at the bottom. So this is zero matrix. If you try to satisfy this definition, okay. So we can say, yeah, it is already in its REF. We don't have to think about other properties.
Okay, sir. Thank you, sir.
Okay, shall we proceed? Okay, right. We can proceed. Yeah, this is so. This is what we have to solve. For example, so 1, 2, 3, and 4. Now, what we want to make it non-zero. Let us keep it, and then here all zero. We want them. So for that, what we have to do? So we need to do R2 minus 2 times R1, then R3 minus R1, and then R4 minus 8 times R1. So all the 3 row operations you are doing together. Now you can just simplify. So if you do that, what it will be? So 2 times 2 minus 2, 0. So 1 minus 2 times 2, so 4. So this becomes minus 3. So 4 minus 2 times 3, that means, so you have to do this calculation in mind, or you can, if you don't want to make any mistake, you write. Okay? You write all the steps. So 4.
Sir, it's R4 minus 4R1, right?
No. 8 R1. I'm R4 is this one row. Okay. Here is 1.
Yeah, but sir, it will be, if we like 4 into 2 will be 8, right? So then it
Yeah,
will
that
be
is also
applicable.
possible. That is also possible. You can also write it. So 4 times R2.
Yeah.
Okay. Why I am writing R1? Because we have selected this row, A11, first row. So everything we will do in terms of R1. So that is why I
Yeah,
have put.
sorry, sir, I was talking about R2. Sorry.
Yeah, no problem. Yeah, you can do that also. R2 you can take. If you take R2, then you have to multiply by 4. Okay.
Sir,
So that is, yeah.
sir, but after doing R2 minus 2 R1, then R2 is changed to 0 minus 3 minus 2 minus 3, no?
Yes, that will happen. So that is why
So that
if you do all the operations in a single step, you
yes.
may get confused.
Then
So that is why,
8R1 is the correct, sir.
okay. So that is why we have to do everything in terms of R1. So R2 minus R1 and R3. This is R3. R4 minus 8 R1. Because you are changing now. Once you do, if you change the new R2, then you have to do what is it? R4 minus R2. Then you can write R2O. That is, let me just write 4 R2 old. You have to write because in the first step you are changing R2. Okay, so that is why if you want to do this, you have to be careful, very, very careful. And this thing you will learn by practice. The more you practice, the more you become comfortable with the operations. So this is minus 4. So this is 4 times 4 minus 2 times 3. So this becomes minus 6. Sorry, minus 6, 4 minus 6, so minus 2. This becomes minus 2. So 5 minus 8 becomes 3. And then 1 minus 1, 0. 5 minus 2, 3. 5 minus 3 becomes 2. 7 minus 4 becomes 3. Then 8 minus 8. 8 into 1, 0. So 1 minus 8 times 2. So this becomes 16. 1 minus 16. So this becomes minus 15. So 14 minus 8 times 3. 8 times 3. So this becomes 10. Minus 10. Minus 10. And then 17. 17 minus 8 times 4. So this becomes 17 minus 32. So minus 15. Okay. So these rough calculations you should do side by side. Otherwise, there is a chance to commit mistakes. So here, what you can do in the next step. So let us write the entries 1, 2, 3, 4. Then 0, minus 3, minus 2, and minus 3. We have 0 already here. Now, if we get 0 here, then we will be very happy. Okay, it will satisfy property 1. So this R2, the new case, every time you can this row will be updated. So that is why it is, though it is customary to write that R2 new is replaced by R2 old plus some RI, okay, some multiplication of. But when you know everything, then you can directly write of this form. So this is R3 in terms of we want 0 here and 0 also here. So for that we have to R3 plus R2. If we do that, so this becomes 0, 0 and 0. And again, if we do R4 plus, not plus, you can say minus 5 times R2. Then again becomes 0, 0 and 0. So this is also is in REF. And rank of A is 2 because only 2 non-zero rows are there. Others. So this task actually becomes easier in order to check whether this row 1, row 2, row 3 and row 4. As you can see, if you try to verify whether these vectors are linearly independent or not, for that you have to solve a system of 4x4 equations. So this little task is telling that here only two vectors are independent. Row vectors are independent. Okay, so that is why this REF concept is very, very important in order to verify whether a given set of a given set of vectors are linearly independent or not. Now, the next question is what will happen if we can verify that these are some given vectors are linearly independent. So you will see their applications eventually. Okay, so these are some you can say more examples. Example. Examine whether the following set of vectors are linearly independent. Or not. So what will happen if the vectors are linearly independent? Then you will have three non-zero rows. Here we have three vectors, three non-zero rows will be there. Here we have four vectors. So we want four non-zero rows. Here we have three vectors. So we want three non-zero rows. If it is satisfied, then we can say these are actually linearly independent. So for that, what we have to do? We have to find out the row echelon form. Okay.
So could you repeat that, the non-zero part?
Yeah. If you go back and check the definition that we have given today, the rank of a matrix, the number of linearly independent rows, and the rank of a matrix can also be defined as the number of non-zero rows in the row echelon form of the given matrix. Okay. In the first class, we have seen if we are given some vectors, what we want to say, we will take the determinant, the vector, okay, n by n. If the determinant is non-zero, then we call it a linearly independent set of vectors. But here we can see that these are, if we take that vectors, then what you will get? 1, 2, 3, 4, then 2, 0, 1, minus 2, then 3, 2, 4, 2. But you cannot take the determinant here because this is not m by n. What is m by n? So here it is 3 by 4. You cannot take the determinant. Determinant is not possible. So if you want to verify this vectors are linearly independent or not, so for that you have to take the matrix, find the row echelon form. Okay. And then
Sir, excuse me, sir.
check how many non-zero rows. Tell me.
Sir, then I guess all row echelon form matrices are linearly independent.
Yeah, okay. All
Row echelon form matrices are linearly independent, sir.
no. Why?
Because row echelon form matrix should have bottom row as 0.
Okay. This is a very interesting question. Okay. I thought to describe, but I forgot to. Whenever you have a vector for v1, v2, and v3, and also, for example, 0, 4 vectors. Okay. Without calculation, you can say this is a linearly dependent set. Why? Because if you take the linear combination C1 plus C2 V2 plus C3 V3 vectors, okay, and C4 0. If you take this one as 0, so at least one, you can see this is already non-zero vector if you assume. So whenever you assume a 0 vector in the given set, so that set becomes linearly dependent. Now, coming back to your question, so you are telling about that all the vectors in the REF are linearly independent, right? That is your claim. Can you repeat, Sairam?
So can we say it's linearly independent if it's a 3x3 matrix or like in
Yes.
n by n form?
Yes, Abhay. What you have observed, that is correct. Okay, so let us see one by one. So Sairam, you can just wait for a few minutes. Then you see these 3 examples. I think your doubt will be clear.
Okay, sir.
Okay. So here, what we do, take the 3 vectors, okay, 1, 2, and 3, write them as a row of a matrix, then take our row operations and try to find out whether this is all the 3 are linearly independent or not. So this set of vectors is not linearly independent. If you have a set of vector of 3, okay, you can call S1 is linearly independent set of vectors if all the vectors are linearly independent. When you take together, so then you can call it a linearly independent. That means if you think about this matrix form, so you will get the 3 rows. This is row 1, row 2, and row 3. So for row 1, row 2, row 3, what we are getting? We are getting only 2 non-zero rows. That means only 2 rows, only 2 vectors will be linearly independent. So that's sort of the first case. If you think about the second case, you can see that we can have the row echelon form, okay, and it has 4 non-zero rows. What is non-zero row? At least one entry is non-zero in the row, then we call it a non-zero row. So this set S2 is a linearly independent set of vectors. Okay, I'm not doing these row operations again. You can see, you can do by yourself just to verify. And if you come back to the third question, the third example, it says it has only 2 non-zero rows. So it is not also linearly independent. So the rank will be 2. From here, rank is 2. Rank of A is 2. Here this rank of A is 4. So here we have rank 3. Is 2. Is your doubt clear now?
Okay, sir. Yes, sir.
Okay, right. So these are some practice problems. Try to verify whether they are linearly independent or not. Okay. Now there is another concept called reduced row, or it is sometimes also row reduced to echelon form, or some authors also write reduced row. It can be exchanged. Okay. Earlier we had only REF. Now we'll have RREF. So what is RREF? It will satisfy property 1, property 2, together with additional 2 conditions will also be there. Property 3 will be there. So each pivot leading non-zero entry is equal to 1. That is each pivot. What is the pivot meaning? Pivot meaning is the leading non-zero entry. Now in RREF it will be 1. And P4, for P4, property 4 is said each pivot is the only non-zero entry in its column. Okay, so if you look at the structure of the RREF matrix, then you will have of this form. Okay, so these are, for example, REF. Okay, these are a structure of the REF. It can be 0. See here, it can be 0 also for REF, as we have seen in the previous examples. And the bottom zeros will be here. The zeros will be at the bottom. So here also zeros will be at the bottom. Okay, if exist. For this particular example, 0 are not there. Okay. So for RREF, it says property 3 says except for each row the leading non-zero entry is 1. If you go back and check the row echelon for matrix, here we have the leading non-zero entries as 1. It can be 5. It can be 3. It can be sometimes negative also. But for row echelon form, it says that for row RREF, it says except that leading non-zero entry, that is the leading non-zero entry. Okay, some authors call it a pivot also. It is also known as pivot. Okay. So this leading entry will be 1. First non-zero leading entry will be 1, and except 1, all others are 0. Okay, 1 is there. In that column, property 4. If you go back and check, property 3 says each pivot, each leading non-zero entry is equal to 1, and except 1, all entries in that particular column is 0. Okay, this pivot is the only non-zero entry in that particular column. So if you think about it, so this is one RREF. So the first row we have 1, second row we have 1, and except 1, all others are 0. Except 1, all others are 0. And it is also satisfying property 1 and 2 also. Property 1 says if 0 row is there, then it will be at the bottom. So it is not satisfied. 0 row is not there, so we don't have to bother about it. What it says, the leading non-zero entry should be right to the previous row. So here it is. 1 is here, and then the right, its right is here. Okay. So it is satisfying property P1, P2, P3, and P4. So P1 is not there. So so it satisfies P2, P3, P4. Okay. Now this question you may ask that whether the row echelon form is unique or not. So there is a theorem which guarantees that the row echelon form of each matrix row equivalent to exactly 1 and only 1. So this would be equal, actually unique. So that is why when we define the rank, let me go back and again. In the, I have used the REF of the given entry. Otherwise, we could have said if it is not unique, then we can say a row echelon form. But it is not applied because this row echelon form is unique for a given matrix. Okay. So here it is. Also, just remark 2, it says the zero matrix and the identity matrix are important special examples of RREF. They are already in the RREF 100, 010, 001. Okay. So they are already in REF. So this is reduced echelon form. Sorry, I made a mistake here. It is not talking, this uniqueness is not talking about the REF. The uniqueness is talking about the RREF. Okay, this RREF. So yeah, in fact, we can get a reduced row echelon form also, that unique also. But this particular theorem says the reduced echelon form, that means RREF, reduced row echelon form. So, for example, if you want to find, if you want to verify which one is a RREF and which one is REF, you can check. If you think about this first example, so 2, the first leading entry is 2. So it is not satisfying P3. Not only P3, it is also not satisfying the P4 also. So it is violating the P3 and P4. Okay. So it is not in RREF, but it satisfies P1 and P2. So this is why it is in REF. How about this one, second example? It satisfies P4, but no, sorry, it satisfies P3, that the leading non-zero entry is 1. Okay, this 1. But it is not satisfying P4. Except 1, there should not be any non-zero entry, but 3 is here. So it is not satisfying P4. So it is not RREF. It is only REF. How about this one? This particular example is both RREF and REF. It satisfies both P3 and P4 also. It is also satisfies P1 and P2 also. Property 1 and property 2 also satisfied. How? See here. So 0, let us keep it as it is. 0 can also be there. We don't have to bother about it. The first leading non-zero entry is 1, except 1, others are 0. Let us come back to the second row. The leading non-zero is here. It is 1. Except 1, the column has no other non-zero entry. Okay. Similarly, for this case, except 1, no other are there. So if you see these examples, then you will get the idea of RREF. So let us see some more examples and how do we get this RREF. Again, by row operation, we can get the RREF. Reduced row echelon form. Okay. How about this matrix? Is it in RREF? Exactly, no. The first leading non-zero entry is 1. Here it is 1, but it has 2 as a non-zero entry in that particular column. So let us recall the people. Okay. So this is not in RREF, but it is in row echelon form. How about these matrices? Are they in RREF? Answer is yes.
Yes, sir.
Okay. This is RREF. This is also RREF.
Yes, sir.
Okay, so this is also RREF. Okay. Now, how do we get that? Again, by row operations. Just now we have seen in this. So I'll send one example that how to get this RREF. Okay. So you try to verify. No need to write in this diagonal position. Okay, you can just write horizontal or vertical also. I have written to, I wanted to actually write all the operations in a single slide. So that is why I have written in a diagonal set. But when you write in your notebook or in exam pattern, you can just write by vertical way, one by one. Okay, just write the operation that you are doing. All the row operations you can do. Just all the row operations you have to write. In each step, I have written only one step. So that is why, so that we do not make any serious mistake. So try to verify.
So could you show the previous slide?
Yes, here it is.
Sir, is RREF is linear independent or dependent, sir?
RREF, see, linearly independent is the vectors. Okay. This particular matrix is not linearly independent. This whole matrix is not linearly independent. Here, what we have only 3 vectors. This is a vector. This is another vector. We have only 3 out of 4. We have only 3 vectors are linearly independent. In this case also, same case also here. Only 3 vectors. But here only 2 vectors. These 2 non-zero vectors in the RREF or in the REF. Okay, in the REF, they are linearly independent. Are you getting the point?
Yes, sir.
Okay, so if you have doubt, you can again ask me. But remember, you take a screenshot, okay, and then ask your doubt. Otherwise, I won't be able to understand. So here it is now. Okay. So try to verify this result, whether I have done correctly or not. Now this idea of RREF will be very, very interesting to know, because Next time we will solve solution this REF and RREF are actually both. This idea will be helpful for finding the solution of a system of a linear equations. Okay, this is just to exactly, yeah, the procedure that you do. This procedure is actually, if you try to find out this RREF, just a minute. Okay. So you can see that this finding the procedure of RREF okay, so this procedure what we have is called finding the REF is known as Gaussian elimination, and finding the RREF is all known as Gauss-Jordan method, Gauss-Jordan elimination. Okay, now we'll discuss something more about them in the next class, that how do we solve actually what is Gauss elimination, what are the advantages of this elimination, and what are the advantages of this elimination, and try to find out how we can get the idea of unique solution, finite number of solution, infinite number of solution, and no solution. Okay, so these ideas will be studied for the next subsequent lectures, and try to find out okay this reduced row echelon form. That means verify. These are possible answers, verify them. They may not be correct, but you have to try whether they are correct or not. So given 4 matrices, try to find the RREF form of the given matrices. I'll stop here today, and regarding this Saturday class, I think it is a repetition of